Good morning, hello, and welcome to the class. Uh, we are at this topic, uh, this one, the fourth order Range Kata method. So this we covered last time, and there are some higher order Range Kata methods as well. Okay, so and then comparison of Range Kata methods. Uh, Now today we will cover the systems of equations. So in systems of equations, we have the situation when we have more than one differential equations in the form dy over dx. Okay, so first differential equation is in the form of dy over dx. So which means that where y1 is the dependent variable and x is the independent variable. The second equation is in the form of dy2 over dx and so on. So these equations can be also solved numerically, okay, and by one of the two approaches. So one approach is the Eulers method. Okay? So in the Eulers method, we apply the Eulers formula to solve the equation. So let's see this example for the solving systems of ordinary differential equations using Eulers method. Solve the following set of differential equations using Eulers method, assuming that at x is equal to 0, y1 is equal to 4, and y2 is equal to 6. So we have two equations in the form of y1 and y2. And their initial values are like that. So x is equal to 0, y1 is equal to 4, for x is equal to 0, y2 is equal to 6. So we integrate to x is equal to 2. So starting from 0, we will integrate to x is equal to 2 with the step size of 0.5. And the equations are dy1 over dx is equal to minus 0.5 y1. And the second equation is dy2 over dx is equal to 4 minus 0.3 y2 minus 0.1 y1. So the application of the Euler's method for these equations is simple. We will just individually apply the Euler's method to both y1 and y2, and then we can one by one we can find the answer. So for example, for the first application, we will get for y1 a value of 3 and the value of y2 will be 6.9. So it will be the gradual application of the Euler's method. And similarly, then using these updated values of 3 and 6.9 for the next iteration, we can find y1 of 1 and the values of y1, y2 of 1 in a similar manner. So maybe I can illustrate it on the Excel. Okay. So for example, over here, for the Eulers, let me first copy it. So this is the problem set. Okay, so for the Euler's method, we will start from x, y1, and then y2. Okay, So x at x is equal to 0, y1 was 4, y2 was 6. And the value of h, the step size was 0.5. 0.5. So for the Eulers method, we find the new value. Okay, we find the new value. So these are, we start from the initial values. So we will find the new value, which will be at x is equal to 0 plus h. That is x is equal to 0.5. So it will be this 0.5. So the new value will be equal to the old value. Old value is this plus the value of dy over dx. So the value of dy over dx for y1 is this. So it is equal to minus 0.5 times y1. So y1 is this value. Okay. So it is like this. Okay, so this is here. And then for this we have, no, it is, remember that for the Eulers method, the formula is, yeah, here I made some mistake. The formula is this one, that is y1 plus function f of x, xy into h. So we have to multiply it by h as well. So because this represents minus 0.5 y1, which is f of xy. Okay, and then this has to be multiplied by h. Okay, h is it has to be multiplied by h. H is here. Okay, and then this is now the correct answer. Okay, so it is 0.3. So can you see this, what I am typing, or it is too small?
You can see.
Okay, you can see it. Okay. Okay, so next for y2, y2 is equal to, it is equal to the previous value of y2 plus the function of xy. So function of xy will be this value. Okay, so I will put it into the bracket. It is equal to 4 minus 0.3 times y2. y2 is this value. Okay, and minus 0.1 times y1. y1 is this value, the previous one. Okay, and then bracket close and multiplied by h. So it will be 6.9. It will be 6.9. So here is also h. So like that. So we have got the values at 3 and 6.9 over here. So 3 and 6.9. Okay, so similarly, then we can expand it. So we can get from x integrate, we can get integrate up to 2. So the last we can just close it. So 3, 6.9, 2.25, 7.715. Yeah, 2.25, 7.75, 1.6875, 8.44, 525, and like that, 1.26 and 9.09. 1.26 and 9.09. So we got the values. So in this way, then we can apply the Eulers method, so which is rather simple to apply. So the second approach for the uh, system of ordinary differential equations is to apply the some order of the Runge-Kutta method. So any of the higher order Runge-Kutta methods in this chapter can be applied to the systems of the equations. However, care must be taken in determining the slopes. Okay. So here you can see that how we can apply the Runge-Kutta methods. So solving the systems of ordinary differential equations using the fourth order Runge-Kutta methods. So use the fourth order Runge-Kutta methods to solve the ordinary differential equations from example 25.9. That means for the previous case. So in this case, we have to apply the Runge-Kutta, fourth order Runge-Kutta methods. So remember that in the fourth order Runge-Kutta methods, we have to calculate K1, K2, K3, K4, okay, by these formulae, okay. So therefore, we have to apply this K1, K2, K3, K4 repeatedly for these two equations. So for this one and for this one, okay. So which will give us like, for example, K11, that is the K1 for the first equation, K1 for the second equation. Then we will calculate the K2 for the first equation, K2 for the second equation in a likewise manner. So in this way, then it will be gradually calculated, and then we will get these values. So you can see that these results are different from the previous result. Of course, more accurate results will be obtained with the fourth order Runge-Kutta methods. So we can also do this on Excel. But for this, we need to find first locate the equations of K1, K2, K3, K4. Okay. So yeah, so this is the fourth order Runge-Kutta method. So I will put it down into the here, and for this is for our and this question is here. Okay, question is here. So suppose we want to apply this Runge-Kutta method. Okay, so in this case now then how will we start? So we will start x, then y1, y2, okay, and then k1, k2, okay, k1 and k2. So x is 0, y1 is, what is y1? 4,
Four,
y2 is
6,
6. Okay, so K1 will be fx1 y1, so it will come from xx1 x1 y1s. So so K1 will be equal to K1 is equal to fx1 y1. So it is okay, so we need to find K1. So K1 is equal to fx1. So fx1 is this one, minus 0.5. So it is minus 0.5 times y1. So it is this. Okay, and so it is K1. So remember that it is K1 of first equation, and then we also have to find K1 of second equation. Okay, K1 of second equation will be equal to this one. Okay, so K1 of the second equation is will be equal to minus 0 point. Sorry, it will be equal to 4 minus 0.3 times y2. Y2 is this, and minus 0.1 times y1 is this. So it was 1.8. So we will get minus 2 and 1.8. So which is the same as over here. Yeah, minus 2 and 1.8. Okay. So these values we will use to find these values we will use to find K2 and K2 of 1 and K2 of 2. But for this, we need to update the values of x1 and y1, okay, first. So where is this? We go back to Excel. Okay, so next we need to find the value of K2. But for K2, we need to have x1 plus h by 2 plus y1 plus 1 by 2 K1 of h. So we will need to find x plus half h, okay, x1, x plus half h. Yeah, in this case, although we need to, you can see that maybe for our, for general case, it's okay, where in these values are in terms of y over here. In for example, these equations are in terms of x and y both here. So we can calculate it. But in this case, this will not apply. But anyway, for general case, we can also put it, although it will make this method a little bit longer. Okay, but anyway, we can apply it. So x1 plus half h, and then we will find the y1, y plus 1 by 2 k1 h. Okay, and similarly, it is for the second equation, y plus 1 by 2 k1. Actually, it is k1 of the second equation h. Okay, and this one is, that is we can say it as y1 plus k1 of the first equation times h. Okay, so means that in just in the case of in the one equation we found it for respectively for that equation. So in the case of the two equation, we will find it for the respectively for those equations. So it, x, the value of x will be 0 plus 1/2 times h. So h is here. Okay, so h, let me put h. H is equal to 0.5. And y1 will be equal to minus 0.5 minus 0.5 times, no. So y1 here. Okay, now we will calculate the value of y1. Okay, so y1 is equal to, sorry, this value we will calculate it. We will calculate it y1 plus half k1 of h. Okay, so it will be calculated as the previous value of y1, that is this original value of y1, that is at the starting, plus 1 divided by 2 times k1, which is this k1 value, multiplied by value of h. So it is 3.5. And then the next value of y plus this is equal to this value of y, okay, for the second one. And then 1 divided by 2 times k1 of 2 times h, this value. So it will be 6.45. So we get 3.5 and 6.45. So this means, let me check it over here. Yeah, 3.5 and 6.45. So we will use these values to find the values of K2 and K22. So now we will find K2 of first equation and K2 of second equation. Okay, so K2 of first equation will be this value of these functions calculated, values of these functions calculated of this for this respective values of x1 and y1. So earlier we calculated it here, and that is with respect to this value, right? And then we are going to calculate it here, and then that will be with respect to this value, right? So here we have this, okay, then we can just copy and paste it. Okay, so Control C, Control V, and then Control C, Control V for copy and paste. So we get minus 1.75 and 1.715, these values. Yeah, minus 1.75 and 1.715. So next, for K3, we will repeat this process. Okay, so for K3, we need to find again these coefficients. So because for K3 is x plus 1/2 h, and then y1 1 plus 1 by 2 K2h. So it is now here we will use a K2 of first equation. Okay, and then here we will use K2 of second equation. Yeah, here K2 of second equation. So K2 of 1, K2 of 2. Okay, so it is equal to x plus 1 by 2 times h is here. And then it is y1. Y1 is here, plus 1 by 2 times K2 of first equation times h is here. So it is 3.56, and then equal to y2. Y2 is here, plus 1 by 2 times K2 of second equation times H. H is here. So here we have calculated these values. So now we can find K3 of first equation and K3 of second equation, okay? And then this we can simply calculate by copy and paste the formulas. So this one, K2 of control C, control V, control C, control V. So now we get these minus 1.78, 1.75, yeah, minus 1.78 and plus 1.715. Okay, and then we have to do it for the K4. So we have to do it K4. So what I will do is, again, I will take copy and paste. Actually, and now it is for K4, it is x1 plus h. Okay, so it is, we can take xi or x1 plus h, and then it is y1 plus K3h, and it is y2 plus, in fact, it is K3 of second equation times h, and then this one is K3 of first equation times h. Okay, so it is equal to x plus h here, and then if this is y1 is 4 plus K3 of first one is this one times h is here. Okay, and then this is y2 plus K3 of second equation is here times h is here. So it is equal to 6 point. Okay. Yeah, and then this one should be 4. Okay, so now we can find the K4 of first equation and K4 of second equation. Okay, so by this just control C, control V. So we can find it 3.01 and 2.3. 3.01 and 2.3, is it same? Yeah. Yeah, it is minus 1.55, and it is, okay, so y1 of this is 3.1 and 6.85. So 3.1 and 6.85. So 3.1 and 6.85. So this is 3.01 and 2.3. I think maybe
pasted incorrectly.
Okay, so let me see what is this here. So it is control C, control V, yeah, and then control C, control V. Yeah, so now it is minus 1.55 and 1.63. Minus 1.55 and 1.63. Okay, so all values we have found correctly. So now we need to, we have already found K1, K2, K3, and K4. So we need to apply it into this equation over here. So I will put it like for x is equal to 0 plus h. So it is this one. So we need to find the y1 and y2. So it is equal to this previous value of y1 plus 1 by 6 times 1 by 6 times bracket k1 of the first equation, k1 of the first equation plus 2 times k2 of the first equation plus 2 times k3 of the first equation and plus k4 of the first equation, bracket close, times h. So h, so whenever I use h, I press F4 to make it as a fixed reference, so that when later on when I copy and paste the values, drag the values for calculating formulas, so the value of h will not change. Okay, so I will press F4 and then I get 3.115. So just check the answer. It is, yeah, 3.115234. And similarly, calculate the for y2, it is equal to this previous value of y plus 1 divided by 6 times bracket k1 of the second equation, k1 of second equation is here, plus 2 times k2 of the second equation plus 2 times, so 2 times k3 of the second equation and plus k4 of the second equation here, bracket close, multiplied by h and press F4 and 6.85. So in this way, I have calculated it. So 3.11 and 6.85. And then now it's the Excel sheet is ready. And now I should be able to calculate these values accurately. So what I can do is I will select it and then I will drag it down. Okay, so now I have the new values of K4 like that. And now I can drag it down. This is 1, 1.5 and then 2. So here I will get these values. The answers. So 6.8, 2.42, 1.7, 7.63. Yeah, 2.42, 7.63. We have next values as 1.88, 8.32. 1.88, 8.32, and then 1.47, 8.94, 1.47, 8.94. So in this way, you can see that we have solved it using Excel. Yeah, anyway. So the solution by hand, of course, will be very time consuming. Actually, for example, in this case, if this type of question is given in the exam, maybe only the first step can be asked. So for example, up to here. So you calculate the values of K1, K2, K4, and then we can find up to this much. So the calculations involved by the hand calculations will be it will take more time. But here we have done it with the Excel, so it is relatively simple once you set up the values, and if you want to repeat it, and then you can just copy and paste up to now, to later. Okay, so this was the this is how you solve this system of the linear equation. But remember that this system of the linear equations you can use, or the previous, any of the previous equations which we use. First of all, the differential equation should be in the dy over dx format. Okay, if the differential equation is not in the dy over dx format, we have to convert it into dy over dx format. That means such as dy over dx is on the left hand side of the equation, and all the other terms are on the right hand side of the equation. Only then we can apply these methods. Okay. So if any equation is not in the form of dy over dx, we have to convert it into dy over dx form first. Okay, so system of linear equations, system of ordinary differential equations, we solved numerically by the Eulers method and by the Runge-Kutta 4 method as well, fourth order Runge-Kutta methods. And similarly, there are computer algorithms for solving the systems of the ordinary differential equations. I will not go through them, but you can try it by yourself on MATLAB. Next, I move to the adaptive Runge-Kutta methods. Okay, so in the adaptive Runge-Kutta methods, the concept is like that. There are some functions which change rapidly at some particular values. Okay, at some particular values. So for those functions, if we apply the normal Runge-Kutta methods or Euler's method, there may be problems, because for that type of function where the value is changing smoothly. So for example, in this part, for this function where the value is changing smoothly, the intervals, that is the step size which we take, is suitable for those type of functions. But when the function is changing rapidly, so we may, if we have some step size such that that step size is not very small, then we may miss many of the points between before the start and after the end of that part of the function where the value of the function is changing rapidly. Okay, so for this we need to have an adaptive Runge-Kutta method. By the adaptive Runge-Kutta method, it means that that method will change the step size accordingly. Okay, so near those areas where the function is changing rapidly, the step size may be decreased accordingly, so that we can find many of these values to accurately find the value of the function in this area where the function is changing the value very rapidly. So for this, there are certain algorithms. So first of such algorithm is that it is called as the adaptive Runge-Kutta or step halving method. Okay, so in the step halving method, it is also called as the adaptive Runge-Kutta method. Involves taking each step twice. Okay, once as a full step and independently as two half steps. So the difference in the two results represents an estimate of the total truncation error. So in this case, we try to find the truncation error in that step, and that truncation error will help us adjusting the step size. So the difference in the two results represent an estimate of the local truncation error. So if Y1 designates the single step prediction and Y2 designates the prediction using the two half steps, So the error can be represented as like this, y2 minus y1. So in addition to providing a criteria for step size control, this equation can also be used to correct the value of the y2 prediction. So for the fourth order Runge-Kutta version, the correction is given by this delta over 15. Okay, that means we find the error and then we divide that error by 15, and then that is added into the value of the y2. So for the correction of the prediction by the y2 prediction. Okay, so this delta over 15, I think this delta over 15 has some derivation, but it is not provided in this book. But anyway, we still can use it. So this is called as the adaptive fourth order Runge-Kutta method. Okay, so in this adaptive fourth order Runge-Kutta method, if you want to correct the second estimate, so we have to apply this method. Okay, so let's see this example. So adaptive fourth order Runge-Kutta method. Use the adaptive fourth order Runge-Kutta method to integrate this 4e power 0.8x minus 0.5y from x is equal to 0 to x is equal to 2 using h is equal to 2, a step size of 2. And an additional condition of y0 is equal to 2, that is the initial condition. This is the same differential equation that was solved previously in example 25.5. And we also know that its true solution at y is equal to 2 is 14.84392. Okay, so if we if we apply the fourth order Runge-Kutta method in this case with the step size of 2, then we will find this solution, which is 15.10584. Okay, 15.10584. So we have already done this type of numerical problem. So first, for the fourth order function, we will find the values of k1, k2, k3, and k4. So the value of k1 will be 3, k2 will be 6.40216, k3 will be 4.70108, and k4 will be 14.11105. So by this k1, k2, k3, and k4, we will find the value of y by the fourth order Runge-Kutta method. So the value will be 15.10584. Remember that in this case, we have taken a step size of 2. And if we are applying this method, so we will find this value at y at 2 by two approaches, okay, by two approaches. One will be a full step size and the other will be with the half step size. So for the full step size, we have found this value 15.1. And if we take the half steps sizes, so in the first step, we find 6.2, that will be the value at y at x is equal to 1. And then secondly, we will find from this half step, so from y is equal to 1, we will reach to y is equal y at x is equal to 2. We will find the value at 14.86. So all these values were found by the Runge-Kutta 4 methods by finding these K1, K2, K3, and K4. So we have found it, we have done this type of question before. So I'm not going to repeat how these calculations will be performed. But anyway, so now we have two values of y2. One is with the single step and the other one is the with the two half steps. So you can see that the we already know the true value over here, 14.84. So you can see that the value which we found by the two half steps, which is 14.86, is much closer than the value which we found by the single step, which is 15.1. So it means that the more accurate value is this by the two half steps. But But by our previous methodology, we can further refine, we can further improve this value of y2 by adding delta over 15 term, where delta is the difference between y2 and y1 values. That is the value which we find from the single step and the value which we find from the two steps. So what we will do over here is that we will take the difference between these two values, 14.86 and 15.1, 14.86 minus 15.1, and then divide by 15. Then we will get minus 0.1622. So this is the estimate of the error. This is the estimate of the error in Y2. And then we can add this estimate of the error in Y2. So it will be 14, it will be 14.86249, and then plus minus 0.01622. So we will get a value of 14.84627. 14.84627. So this will be the better approximation for this y2 value over here. This will be the better approximation, and then it is much closer to the true value, which was 14.84392. Okay, which is 14.84392. So in this way, this adaptive fourth order Rang-Kata method works. So the main thing to remember in this method is that first we will find the value of the function by the full step, and then we will find the value of the function by two half steps, and then we take the difference between these two values and then add that difference between these two values by the to the second value to find the refined estimates of the second value. So this is the application of the adaptive fourth order Rang-Kata method. Another approach is called as the Rang-Kata-Fehlberg method. Rang-Kata-Fehlberg method. So in the Rang-Kata-Fehlberg method, it is a series of equations in which we need to find the 6k values: k1, k2, k3, k4, k5, and k6. In fact, this is this is a refined approach for the alternative method, in which we have to find the 10 functional values. So as we can see that aside from step halving as a strategy to adjust the step size, an alternative approach for obtaining an error estimate involves computing two RK predictions of differential order. The results can then be subtracted to obtain an estimate of the local truncation error. The one shortcoming of this approach is that it greatly increases the computational overhead. For example, a fourth and fifth order prediction amounts to a total of 10 function values per step. However, Rang-Kata-Fehlberg or embedded RK method cleverly circumvents this problem, and using a fifth order Rang-Kata method that employs the function evaluations from the accompanying fourth order Rang-Kata methods. So thus the approach yields the error estimate on the basis of only 6 function evaluations. So Rang-Kata-Fehlberg method is an improvement over a method in which we have to find the 10 evaluations. So instead of 10 evaluations, we need to find only the 6 evaluations. And those 6 evaluations are given by these terms. So here in this case, we can find the values y1, yi of 1 by one equation, and then we can also find the value of yi of 1 by this second equation. The first is the fourth order estimate. So we can also find the fifth order estimate. So we can find the fourth order estimate and the fifth order estimates. In order to find these fourth order and the fifth order estimates, we need to determine the values of K1, K2, K3, K4, and K up to K6 by using these equations. Okay, so we will first find the the values from K1 to K6 by using these equations, and we will find the fourth and fifth order estimates. And the difference between fourth and fifth order estimates will be then found out. So thus the ordinary differential equation can be solved with the equation with these equations, and the error estimated as the difference of the first and the fourth order estimates. So it should be noted that the particular coefficients used above were developed by Cash and Karp in 1990. So therefore, it is sometimes called as the Cash-Karp-RK method. Okay, so Runge-Kuttak-Fehlberg method or the Cash-Karp-RK method can be calculated as here. So since in this case the calculations involved are quite a lot, last time I did it on MATLAB. It was example, what is that? Example, this is example 2513, okay, 2513, not on MATLAB. Example 2513 on MATLAB. Where is this? Oh yeah, this RK Fehlberg method. So for this RK Fehlberg method, so you can just make a script for the values of K1, K2, K3, K4, and when you run that script over here, and then you can find these values of X, Y, and K1, K2, K3, K4. So fourth order prediction and the fifth order predictions. Okay. So here we can see that I got the same values. So you can program it in the MATLAB as well. I think you can also even do it on Excel as well. But I will not do it because the calculations involved are tremendous, and then it will take much time to do it. Okay, but as I have done it for the previous cases, for the fourth order Runge-Kuttak method, so the pattern is the same. Only thing is that we are using bigger numbers and then fractions over here. All right, so I think we have almost completed this chapter. So I will I stop at this time, and we will finish it in the next week on Monday.